So today we will talk about Advanced Encryption Standard, which is the most widely used encryption standard, as far as I know, today in modern systems. So its name is AES. It's like, AES encryption. So if I Google this AES, it says Advanced Encryption Standard. Well, I'll first talk about the name. Why Advanced Encryption Standard? Well, because before this encryption standard, there was DES, which was, let's see, it was Data Encryption Standard. It was a very good, very smart way of encrypting data. So it was just called Data Encryption Standard because it was one of the first encryption methods that was widely approved and certified. So basically, in 1970s, when the computers were really slow, people came up with this data encryption standard, and it and the good thing about this encryption standard was it was public. People checked it out. People tried to break it. They decided that it is pretty strong. So it was also approved by, for example, United States National Security Agency, right? So and it was also approved by National Bureau of Standards. Um, it was like widely approved standard encryption. This is why it's called data encryption standard, not just simply data encryption. And it was used in many, many systems. Um, just a few words about data encryption standard. Um, it works on blocks, so you cannot encrypt one bit. You can only encrypt the blocks of 64 bits. So if we take 64 divide by 8 bits per byte, it encrypts blocks of 8 bytes. So if you, for example, have 6 bytes to encrypt, you just add, for example, 2 zeros at the end. You just pad it. And yeah, it works on 64 bits. And the password or key length is just 56 bits. So for 1970s, 56 bits was actually a very large number. But because the computers got faster and faster, and we have interconnected computers, and for example, hackers can plant viruses in many hundreds or thousands of computers and ask them to each check only part of the passwords, using this distributed computation. uh, 56 bits is just nowadays considered to be too short. The algorithm itself is actually pretty good, pretty smart, but the passwords are just too short for valid encryption. So for example, what does it mean 56-bit key? So it means that password length is 56 bits, so we have 2 to the power of 56 different combinations. A large number. In 1970s, going through each possible combination would be just impossible. Computers running on 33 megahertz, just not possible. So let's say this is the number of all possible values of the passwords, and we want to run through all of them and find which one is the correct one. So let's say we have in 1970s a computer that runs on 33 megahertz, and for example, it takes, I don't know, maybe there is hardware acceleration, it maybe takes 33 clock cycles to do one encryption. So it basically is 1 million tries per second. So I divide it with 1 million. And then this is how many seconds you would need on such computer to go through all of them. So divide by 60 is minutes, divide by 60 is hours, divided by 24 is days, divided by 356, 65, sorry. This many years, 284 years for 1970s computer to try all possible passwords out. And 2000 years is longer than any person has lived. You know, people's life expectancy is something like 84 years. So you have 2,200 more years than before, you can get a result. So in 1970s, it was considered like super strong, good encryption algorithm. Today, the computers run something like 100 times faster. So instead of 2,284 years, 100 times faster computer does it 100 times faster, so 22 years. And computers are connected over the internet. So you can have, for example, 22 computers with a virus, each computer checking only small fraction of the possible passwords. So you divide this with 22, and within 1 year you can get you can crack this. If it's top secret American secrets, then you can wait 1 year. It's not a big deal. But if you connect 1,000 computers, well, then you divide it even more, for example, by 50, and then within a month you can get cycle through it. So this DES is just considered to have too short password, so it's not used anymore. But generally it was a good thing. So here is a very good example. So in 1970s it was impossible to crack it, but then at one point there was actually a competition for a small prize of who is going to crack this data encryption standard. I think that the prize was something like $10,000. So the company that published this data encryption standard, they set a $10,000 bounty to or reward to a group or a person that somehow cracks this algorithm. And what happened was one company just made a board. Well, actually, this is just one board, but they made something like 100 such boards, each of them containing something like 1, 2, 3, 4, 5, 5 times 1, 2, 3, 4, 5, 6, 30 CPUs. And you have, for example, 100 boards running in parallel, and they just calculate, each of them just calculates one part of the password, one part of the password set, and eventually they just crack it. So using these small microcontrollers, each searching for only part of the password space, it was able to crack this DES using brute force attack, nothing fancy, just trying all possible passwords within, I think, something like a day. Oh no, within 7 hours. Well, the problem was that such machine cost $1 million because it contained many, many, many chips. Um, so, you get 10,000 euro reward for building a machine that costs 1 million. But it just was proven that you can crack it. So not really talking about this DES much. DES was superseded by AES. So that was data encryption standard, and this is the advanced encryption standard. So compared to data encryption standard, this is advanced. And well, first thing is that the AES has longer keys, longer passwords. So minimum, basically, just three possibilities: 128 bits. So it is 2 times longer, but each bit doubles complexity. So it is 2 to the power of 64 times more complicated. So it's not that you make a password 2 times longer, it becomes 2 times more complicated. No, it rises exponentially. So it makes it 2 to the power of 64 more complicated. Or the key can also be 192 bits or 256 bits. So 128 bits is plenty. It's impossible to calculate it within millions of years. But because there's a possibility that quantum computers will be much, much faster than the computers that we have today, so um, the creators of this algorithm kind of expect it. So they also have 256-bit keys, which are exponentially much more complicated than 128-bit keys. And it is assumed that even quantum computers will have big problems calculating or cycling through 256-bit keys. It will take billions of years for quantum computers anyway. So if you want to make like super, super strong encryption, just use 256-bit keys. But 128 is considered very safe anyway. So let's just talk about this advanced encryption standard. So first of all, um, advanced encryption standard works on blocks of 128 bits. Or it's the same as 16 bytes. So if you want to encrypt only less bytes, you need to add some zeros at the end. So if you want to download a movie over secure connection, the movie, those gigabytes of data will be split into pieces of 16 bytes, and each of these pieces will be encrypted separately, sent, then you receive it, and you decrypt them by 16-byte blocks. So key size is 128 or 192 or 256 bits, which is basically equal to 16 or 24 or 32 bytes. Okay. And now let's look at how this algorithm works. So basically, this block cipher is just, for users, is just a black box with name AES on it. And it has the following inputs. You give it block of plain text, and you give it also the key. You tell it the password, and you select direction, because encryption and decryption differ a little bit. So you give it plain text, you give it key, and you switch between encryption and decryption, and the result is ciphertext. And the algorithm works, well, it's basically based on substitution based on the password. Substitution helps reduce non-linearity, reduce the linearity. It increases non-linearity because when you do some XORs or something like that, it just can happen that, it's not such a strong encryption. So we have something in the chat. So direction. Um, the direction selects between encryption and decryption. So in an encryption case, the direction will be forward, which is encrypt, and you switch it to decryption mode, and it calculates back from ciphertext to plain text. Oops. So I hope I answered the question. Yes, I know. Okay, yeah. So let's look at how this algorithm works. Actually, here are some beautiful pictures. So the first step is key expansion. So basically, you have a password, which is, for example, 128 bits. And first, it is expanded, it's made longer. But you can imagine it as just take the password and just copy it, for example, 5 times. So it becomes 5 times longer. But to hide the password, it's actually expanded a little bit more differently. So key expansion happens by just selecting some bits of the password and repeating them, and then some other bits of the password and repeating those as well, and using a little bit of substitution. Just make the password longer, but instead of just repeating the password n times, it goes through some bit mixing algorithm as well. But maybe it's not that important. It just, you get it longer. And then we have the following algorithm. So each byte says, the first step of this algorithm, without some beginning and ending nuances, is substitute bytes step. So the idea is the following. We write our 16 bytes as a table of 4 by 4. So byte 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So we write them in this table form. And the first step is just replace the bytes using a lookup table called Reendial S box. So basically, and also this Reendial S box is public. You can see it right here. This is the S box. So for example, if the original byte so if the original byte is, for example, 5D, then in row 5, column D, you can find that 5D is replaced by 4C. It's just copy pasting over the original data. So if data is, for example, 0, 0, replace it with 6, 3. If data is A9, then replace it with D3. So this way, you had some original data, and now it's just replaced by new data according to this table. So that is the first step. Quite simple. And the reason for it is that these values, this table is fixed and everybody knows it, it's public, but it's mixed in such a way that there's no linearity between input and output. This table cannot be expressed using some mathematical formula. So you cannot, for example, take the input, multiply it with something, divide it with something, and then get the result from this table. It's impossible. This table is hand-picked in such a way that there's practically no linearity, no connection between input and output, so that this algorithm cannot be replaced by some mathematical formula. Because if it could be replaced with a mathematical formula, then the output would correlate with input and the algorithm would be weak, because you could find some connection between output and input and break it. So for this reason, the algorithm is not based on some linearity. It is based on non-linear, uncorrelated, totally unrelated input-output replacement. So that is the first step, which is substitute bytes using this lookup table, which is mastered to have no linearity between input and output. So we just substitute the bytes. Next step is shift rows. So basically what happens is the first row is not touched at all. The second row is just all bytes are, shifted by one position, and the last byte is just written to the beginning. In the next row, they are shifted by two, so all bytes are moved forward two positions, and the last byte is shifted into the second position, and the third byte is shifted two positions ahead. It goes to the beginning. And the third row is shifted by three, so all bytes are shifted by three positions ahead. So this last byte becomes the first one. This is shifted by 1, 2, and 3. This byte is shifted 1, 2, 3, comes to the beginning. So, this is the shift rows step. And then the next step is mix columns. And columns are mixed and also multiplied with a fixed polynomial Cx. So not only are the columns changed by their locations, so in the mixed column step, the 4 bytes of each column in the state are combined using an invertible linear transformation. So in this case, there's a linear transformation, but it still helps mixing the bits. So mixed column function takes 4 bytes as input and outputs 4 bytes, where each input byte affects all 4 output bytes. So together with shift rows, mixed columns provides diffusion in the cipher. So for example, so basically each column is just multiplied with this fixed matrix. But what it does is, if, for example, this byte A is all zeros, it can happen that it just produces the same output every time. For example, here, let's say that the first row is just all zeros. Then in substitute bytes step, all of these zeros will be replaced with all of the same new values. For example, 0, 0 is replaced by 6, 3. So these guys will be all replaced by 6, 3. So they will be the same and you can mix them. There's no change. And what this step does is it mixes the first byte with all other bytes using this matrix. So these bits across the column are mixed and smeared all over so that you get some, diffusion of all of the same data over several bytes. So it's just linear transformation, but it helps transfer some equivalent equal bits to other locations so that you don't get, a loop where basically nothing changes. So this mixed column step is column multiplied by this matrix, and the result is put in the same column. And then the final step is add round key step, where basically the shifted row and mixed column table is XOR'd with the password. But as I said, instead of XORing with the password itself, the password was first sent to this key expansion algorithm. So the first step was key expansion. So you take some bits of the password, you repeat them, you do some S-boxing on the password, and you basically get several tables of expanded password. And each of these password expansion blocks is XOR'd with the input, and you get the output. So basically, input data before adding password isn't really encrypted. It's just copy, paste, replaced, and diffused. But here in this step, this is where the password comes in. And if you have wrong password, you will have wrong key expansion box. You will XOR with the wrong number, and you will get the wrong result. So this is where the password or the key is used. Okay, so this is the process, but doing this just once wouldn't really be secure. To make it everything more complicated, these steps are repeated several times, and actually the number of rounds, each of these steps is called round. If you use 128-bit key, it's repeated 10 times. If you use 192-bit key, it's repeated 12 times. And if you use 256-bit password, then it's repeated 14 times. So each of these times is complicated to calculate, but if you repeat it 12 times or 14 times or 10 times, then it's really, really hard to calculate something backwards. So you substitute bytes using this nonlinear S lookup table, then you shift rows, then you mix columns with this constant matrix, and then you XOR each byte with part of the password expansion, and you repeat it, for example, 10 times. So it's really, really hard to calculate it backwards. If you don't have a password, you cannot even calculate backwards the first step, which would be XORing output with key to get the input, and then to mix it back, and then to shift it back, and then to substitute it backwards using this lookup table in reverse mode, right? So basically, this algorithm makes sure that input is not correlated to the output, that long lines of zeros or ones are diffused all over the ciphertext, and long passwords make sure that you cannot guess the password just with brute force trying all possible passwords that are possible. So this algorithm was published, and it was invented by two people called, where are they? So they were developed by two Belgian cryptographers, Vincent Riemann and John Diemen, and they submitted it to National Institute of Standards and Technology, and it was a little bit changed, and now it is used as encryption algorithm. Okay. Now let's analyze this algorithm from the hardware perspective, The good thing about this algorithm is that it can be easily implemented inside the computer. You can calculate it mathematically. You go through each byte, replace it in the lookup table, mix the shift rows, mix columns, and then XOR. And you can write a code that does it, but it's also possible to make hardware acceleration for this, basically implementing some hardware that does it automatically online really fast without programming. So you just give it the table, the password, and it just automatically calculates everything in hardware and gives you the output within, a couple of clock cycles. Since this algorithm is published, anyone can try to break it. And I wouldn't be surprised if there was a financial reward to anyone who would break this cipher. And breaking would mean come up with some method to guess the password faster than 1 million years. So if you, for example, could create a machine or algorithm that can guess the password within, for example, a couple of months, then you would be famous. Maybe you would also get some financial reward. So this algorithm is widely analyzed. So there are some known attacks on this algorithm. First one is brute force attack, but we calculated that it takes millions of years on millions of computers running at millions of tries per second because the passwords are so long. So, so some known attacks reduce complexity from 2 to the power of 128 to, for example, 2 to the power of 99.5. However, 2 to the power of 99.5 is still extremely big number. So even this security is strong. So if you get something like 2 to the power of 80, it's still pretty strong. So as long as this number doesn't drop under 80, you can say that the encryption algorithm is still strong. And some other attacks, for example, there are some theoretical attacks that reduce complexity to 2 to the power of 88, but such algorithms, the problem with them is that you need several hundreds of terabytes of memory to store some caching data while you calculate the attack. So for example, you need 9,000 terabytes to implement this theoretical algorithm, which reduces the complexity to the power of 88. So, there are some theoretical attacks, but they are not really practical. You cannot really implement them. Okay. Another attack that is possible on this algorithm comes from side channel attacks. And these attacks depend on the implementation of the algorithm. So here's the deal. If you write this algorithm yourself in some programming language, it is possible that you, for example, write some ifs or something like that, and depending on the input data, if you write it in a wrong manner, it can happen that for some bits, the encryption happens faster, and for some other combinations, it happens slower. This algorithm kind of actually doesn't have such property, but it's possible that, you just implement it wrongly. and hackers can use it. For example, encryption of a 0 happens faster than encryption of 1, so the hacker steals the device and measures how long the encryption took and makes some assumptions from that. This algorithm doesn't have any ifs. It works pretty much constantly on everything, but there's a different side channel attack that is possible if this algorithm is implemented in a wrong manner, and it has something to do with, for example, power consumption of the processor that encrypts the data. And the problem could be, for example, that if input is all zeros, then the processor consumes less energy, and if input is all ones, high, maybe the processor consumes more energy. So this is another side channel attack. You have no control over it. It's on the shoulders of chip implementers, chip processor manufacturers, to make sure that power consumption of the encryption engine doesn't differ based on the inputs. And actually, there are some algorithms that actually measure electricity, and if it's consumed more, then it means there are more ones, and if it consumes less, then it's more zeros, and hacker can actually use that information. So chip manufacturers try to make sure that the chip consumes constant amount of power regardless of input data or password data contents. Okay. So here are some examples of side channel attacks. There are cache timing attacks, where some computers cache some parts of key, and depending on how fast it says a reply, for example, successful connection or unsuccessful connection, hacker can determine how much of the password was correct. Cache timing attacks. This is on the shoulders of server implementers. You cannot really influence it. Okay, but now let's just do some practical things, and let's try to encrypt and decrypt some information using Advanced Encryption Standard. And let's check out if we can make some things out of it. So Advanced Encryption Standard is open standard. You can go online, and you can even find online AES encryption websites. So AES online calculator. Okay, online calculator as one word. So here you have AES online calculator, and you can actually go to some web page, and it has, for example, AES encryption and decryption, test software. So let's just check it out. Maybe it's possible to use. So enter text to be encrypted. For example, a secret message. As I said, block size needs to be 16 bytes. So we need to write a text which has 16 bytes length, or 32 bytes length, or 48 bytes length, and so on. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this text is 16 letters, so it's 16 bytes, and we can encrypt it as one block. Then key size, for example, 128, and enter secret key. So the secret key needs to be 16 bytes sharp. So for example, my secret password. Let's count the characters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so my secret password is 16 bytes. So the result, well, we will just select hex. The result will not be human readable because it will be just ones and zeros almost randomly. It will look like random ones and zeros because encryption is so strong that you cannot read the text. It's encrypted. So if I press encrypt, let's see how many bytes it produced. Okay, there's a problem that this text automatically adds 0 at the end. So actually we need to input 15 bytes. So, so if I add 1, it automatically expands it to 2 blocks. So I just short, this is like just implementation issue. So I give it some text, I give it a password, and it encrypts. And what it gives out is 16 bytes of hexadecimal output. So it should be 32 letters. So it's 32 characters. Okay. Now, when I hit encrypt, then this thing just calculates AES output. And this is that AES output. It took the input text, it took the password, it expanded the key to 10 times the length because it has 10 rounds using 128-bit key. And it took the message, it shifted rows, mixed columns, then it XOR'd the data with part of the secret key and did it 10 times, and this is the output. And if I gave you this output, let's check it out. I paste it here. The input is hex. Now I will try to decrypt it. So this is the ciphertext that I got as output from encryption. I put it here, and then I selected this hex. Encryption mode doesn't matter. Key size in bits 128, and I take the same password and I hit decrypt. Unfortunately, oh yeah, there is this base 64 format, but we want to decode it to plain text. So this is the plain text. Because encryption can be done not only on text, but also on movies or audio. So audio will be some ones and zeros which are non-readable. So this is why there is this base 64 format. But generally, this page allows us to convert it back to plain text. So this is the algorithm. Message, password, encrypt, take the output at the other end, put the same secret key, and decrypt and decode the plain text. Now, let's say I have a wrong password. Instead of my secret password with low D, let's say, for example, that the hacker thinks that the password is my secret password with capital D at the end. If it hits decrypt, it even gives out an error, which is stupid. This algorithm implementation is bad. So yeah, this web page is not very great because if you give a wrong password, the algorithm shouldn't really give you an error. It should just calculate output in a wrong manner. So let's try to use a different page. This was a bad web page. Lots of advertisements. So input type is text. I'll just write it plain text. I'll try it once more. So my secret message is plain text. Function is Advanced Encryption Standard. Password is my secret password. And I click encrypt. Yes, this web page is put extra character, but you know, it's website implementation. Okay, so I encrypt it and I get this output. So you are asking what is ECB?
The method of encryption, is it like, same in all the websites, or it varies from each and everything?
So if you're asking about what is ECB, then it is mode of operation, and we will study about modes of operation in the next lesson. Right now, let's just use ECB, which is default basic, very simple implementation of the encryption.
Okay.
For the sake of this lesson. So when we encrypt our data, we get this output, which is really strange because it's different from this. So these two websites, so this website probably is wrong. So, oh, these free online encryption calculators are just so wrong. Okay. Okay, I'll try to do it in this web page. So if I take encrypted text, so this is ciphertext, and I paste it here, and I hit decrypt, then as you can see, it decrypted correctly to my secret message. So this works like this. And as I was trying to show you on that other web page, if I change the password and hit decrypt, I changed just one letter inside the password, and as you can see, all bytes are calculated wrong. So the original text was my secret message, but just changing one bit in a password, the output is totally different. So this is the positive good thing about Advanced Encryption Standard, which should be true to all encryption algorithms. If you have just one bit wrong inside the password, so instead of my secret password, it had capital D, uh, then the output is not only just some parts of it decrypted in a wrong manner, but all of the output is wrong. So, I don't know, in the beginning, instead of small m, I have capital M decrypt. As you can see, all bits are wrong, unreadable, and it's impossible to figure out what the original message was if you have a wrong password, if you have just one bit wrong inside the password. So this advanced encryption standard is developed in such way that one wrong bit inside the key results in totally different, totally wrong entire plain text. So this is Advanced Encryption Standard. So let's try something more. So let's say we have a sensor which sends data, for example, once every 5 minutes. And it says, for example, whether there is motion or there's no motion. So the text will be motion detected. And I have some secret password and it encrypts. So the ciphertext looks like this. I can copy it. I can paste it here. It's hex and I hit decrypt and it says motion detected. So I encrypt, the sensor encrypted the data. It sent it to, for example, my cell phone. My cell phone knows the password. I gave it the same password as sensor and I can read the message. The hacker cannot read the message because the hacker sees ciphertext. He doesn't know the password. So it's impossible for hacker to know whether there was motion or wasn't, right? So before we go ahead and talk about modes of operation, which is a very big topic, let's first look at some side channel attacks on encryption algorithms, which maybe will be very interesting for you. So side channel attacks. Okay, so in a computer security, side channel attack is attack based on information gained from the implementation of system rather than weakness in the implementation algorithm itself. So advanced encryption standard and actually many other encryption algorithms by their design are strong, but it just can happen that the implementation of the algorithm is weak. So for example, here is a picture, an attempt to decode RSA key bits using power analysis. The left peak represents CPU power variations during the step of the algorithm without multiplication, the right peak step with multiplication, allowing an attacker to read bits 0 and 1. So this RSA algorithm, even though it is theoretically strong, it's based on the following thing. If bit is 0, then don't do multiplication. And if it's 1, then do multiplication. As a result, if the bit is 1, there will be higher power consumption. And you can see it here. And if bit is 0, then there will be smaller power consumption. And you can actually kind of catch the power consumption. You can catch approximately what is the bit width of each bit. So here you can see it's 2 ones, then 2 zeros, then 1, 2, 3, 4 ones, then 0 again. And based on power consumption, hacker can actually figure out what the password is. And it is especially important, for example, for card readers. You know, you go to the shop and you, for example, beep your credit card or insert it inside this payment terminal. And the payment terminal needs to be made in such way that such attacks are impossible because, for example, you can open a shop, you can get the card reader, then you can secretly connect it to this power analyzer and logger, and you can just acquire credit card information from this. And then you can send such signals again, and the bank will credit you several times to your bank account, basically, knowing this information. So this is one good example of side channel attack. So power monitoring attack is one of the methods. So this thing needs to be taken into account by the silicon manufacturers, by Intel or STM or Silicon Labs or any other company that creates microcontrollers and chips. Okay. So next attack is timing attack. So oftentimes when you connect to the remote server, you try to do a connection, and for example, you try to connect to Facebook with the wrong password. So Facebook receives your request, and then it compares the password that you send with the password that it has stored in its servers. And here you can have a timing attack in the following manner, which was actually a real attack on TLS version 1.1 or something like that. Let's say your password is my secret password. That's not my actual Facebook password, by the way. So the password is my secret password. The hacker sends something like A, B, C, D, E, F, G, H, I, J, K, L. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. It will be 15, 16 bytes. So a bad implementation which opens a timing attack vulnerability would be the following. So server knows that this is the correct password and you send a wrong password. So bad implementation is the following. The server takes the first a letter and it sees that it's wrong, so it sends back that, for example, text password wrong, or log in with different password or something like that. So now you try to send text, for example, all B's. The server checks out the first letter, it says, wrong password, and sends wrong password again. Then you try all C's, all letters C. It checks out that is wrong, it says wrong password back. Now you repeat it. I'll not write all of the possible combinations, but if you send all letters M, check out what happens. The server compares M is correct, and then it compares the next letter Y, but it actually when it compares the next letter, it only then sends that it's wrong password. And what happens is you receive the reply a little bit later because the first letter was correct, but the second was incorrect. But before it, the first letter right away was incorrect. So it compared the first letter, it was wrong. It sent the answer immediately. But later, when you send the first letter correctly, it compared it, it was correct. And it sent the wrong password only after the second comparison, which actually took something like 1 microsecond more time. So the hacker just measures how quickly it receives the answer that there was a wrong password. And it sees, okay, at letter M, suddenly I start to get reply 1 microsecond later. And with modern technology, with modern computers and modern microcontrollers and timing devices, you can calculate, you can measure time with precision of nanoseconds. So actually, it is possible in some cases, to measure how quickly you got the wrong password reply. And basically, when the hacker sees that it starts to get reply a little bit later, it knows that the first letter is correct and the reply was based on the second letter. So it just tries all possible second letters, and when it guesses correctly M and Y, then it starts to get a wrong password reply even later, because then it's sent only after the third letter is detected wrong. So, for example, the hacker measures that first letter is M, second is Y, and then it tries this third letter. So A, it receives wrong password, B, it receives wrong password again, and so on and so on. And when it guesses correctly that third letter is S, then it receives wrong password on the fourth letter. So it comes even later by 1 microsecond or something like that. So hacker can measure how quickly it receives a wrong password message back and guess the password letter by letter. And this was actually a real problem in older computers. In modern computers, they run on several gigahertz of speed, so maybe it's not really possible to measure the time. But on older implementations, the encryption was calculated on the entire block, and you send several blocks, and the first block was wrong, so you get the wrong password answer immediately. But you try all possible blocks, at some point it's correct. So the second block of data is wrong, and then you get wrong password reply later, so you know that first block was correct, and so on. So this is a timing attack, and this helps hackers to guess the passwords or the encrypted ciphertexts and so on. And this is, even a more serious problem. So nowadays, computer systems are built in such a way that the result is calculated on all text, on all letters, and only then the result is sent as wrong password or correct password. So that hackers cannot use this, that, oh, the first letter was wrong, I received reply earlier, and if it's correct and the mistake is somewhere later, then I get the reply later in time. So this is timing attack. It's a real problem. It's possible to actually measure it. So in real life, sometimes the server implementation actually deliberately waits some random time of milliseconds before sending this answer wrong password, so that the hacker doesn't know at which precise time the mismatch was detected. So either calculate password on the entire data and then send wrong password reply, then it will take constant time. Or if you want to drive the hacker really crazy, add some random delay and only then send the wrong password reply. Then hacker really doesn't know, did it guess correctly or did it not guess correctly, because this time will vary every time. So this is timing attack on the implementation of cryptography algorithm. So here also avoidance. And we always want the computer to calculate things as fast as possible, but in this case, unfortunately, it can backfire and work in against our will. So another attack is electromagnetic attack. It's similar to power monitoring attack, where basically when we send ones and zeros, there is some electromagnetic waves leaked, and then we can measure it and get some information about plaintext or ciphertext or something else. This is why the devices that are, for example, in payment systems or places like that, they should all be grounded, earthed, and magnetically shielded so that there's no um, leakage of electromagnetic signals. So, for example, point of sale systems, which are the payment system card readers in shops. So one problem is, for example, in this, when you beep your card wirelessly, you put it next to the card reader, and using near field communication, it reads the card number. Well, the problem is that somebody can, put some coil nearby and read these ones and zeros. And this is why most card issuers set a limit of 25 euros when using a wireless near field communication card. So if you want to make a greater purchase, not only do you beep the card so its number is written down, but you also need to input the PIN code by hand, and the PIN code is not visible to induction sensors. But let's just check out. So when the smart card information is read, it's read over this I2C interface. So you have supply, you have ground, and there is clock and data. So every time a clock goes high, low, there is changing electromagnetic field. So a coil that is located nearby can, or some very sensitive amplifier, can catch these ones and zeros and get the clock and also the data. When it goes high or low, it also emits a little bit of radiation, so it can also be read. You need to tamper with the device, you need to put the sensor equipment very close because the signal is really weak, but theoretically it's possible. And this is why there are some companies, like for example Wood Electronic, which sell special material, which is EMC components, um, shielding, and they sell two kinds of shielding. One is metal shielding, so right here, uh, shielding cabinets, which you can put on top of the chip, so electric field is trapped inside and you cannot sense electric component. And the second way is magnetic shielding, which absorbs magnetic field, and the magnetic field doesn't get out of the device. So if you're building like military grade super secure devices that you don't want to leak any ones and zeros, any bits, you can buy these magnetic materials, ferrites, and the magnetic field, as it radiates off the PCB, it will just go through, it will be absorbed by this magnetic material.
Professor, but this magnetic field shield, it's really expensive, isn't it?
Actually, it's not really that expensive. These sheets, they cost, I don't know, maybe a couple of cents per piece, maybe something like a euro or two per square meter. But using 1 square meter, you can actually coat several devices. So it's not really that expensive. It consists of a ferrite powder, which is mixed with, for example, plastics and created in these sheets, which are actually thin. Their thickness is, for example, 1.5 millimeters. And it also has one side has double-sided tape, so you can just glue it to the internal parts of the case, or you can glue it right away on the PCB. And yeah, it costs €1 or €2, but you know, it's not like millions of euros. It's not some NASA space technology. So, you know, it's not that expensive. But yeah, it of course adds cost. So if you are making simple devices, you don't really need them. But for payment systems, something like that, you would want to use such things. So this is electromagnetic. Yeah, again, this RSA algorithm, as strong as it is, because it has some ifs and branches, you can measure also electromagnetic parts, components, and get some information. So there's also acoustic cryptanalysis, and the problem with that is okay, so theoretically, somebody can, for example, listen to your keyboard, and different keys produce a little bit different tones. So as you type, so maybe they can that way somehow get your passwords. You know, it's not really that easy to do it, but you know, theoretically it's possible. So,
This is also used in like deriving the ATM password, right? Like while typing the pin on the ATM machine, like it
oh.
produces sound and
Yes, exactly. It can be used there, you know. So what people try to do when they build these machines, they try to make the keys as silent as possible, and also put some rubber or some cushion so that, you know, they don't produce much sound. So there's also differential fault analysis. Actually, differential fault analysis is something which is pretty smart. So yes, you're asking a good question. So in these card readers, you would not put a shield on the side where you put the card. So of course, then the magnetic waves wouldn't go through the card and wouldn't be able to read the card number. So yes, you would want to coat all sides of a device that does not have the wireless card reader, but on the wireless card reader, you would coat the sides and the bottom part so that somebody cannot hide, for example, this interception device under your card reader. So, you know, if somebody puts some magnetic coil under it, it's shielded from the bottom, so the hacker wouldn't be able to read the data. So yeah, you wouldn't put it on the top part of this wireless machine. So good question. This differential fault analysis basically works by deliberately sending wrong data to the device and then checking out what the reply would be, right? For example, a smart card containing an embedded processor, you put it to high temperature, wrong supply voltage, something like that. And then maybe it's possible to get some kind of ones and zeros read out. And some of these have actually been used. And also data remnants attack. So for example, if you have files on your hard drive, when you press delete in Windows, the file isn't really physically deleted from the hard drive. That location in the hard drive is just marked as old data, which can be used for some new files, but to save the life of hard drive, it's not really deleted until it's really necessary to delete. So for example, hard drives can still contain even deleted files, as you know. That is one case of data remnants. And another is when you reset computer, the random access memory is not deleted, and maybe it has some passwords from previous boot up, and some viruses can actually try to use this thing, and so on. So side channel attacks are uh, pretty serious. And another side channel attack is ATM infrared. I wonder if we will see some pictures with that. So the idea is you enter PIN code, and as you touch the PIN, these buttons, your finger heats the buttons up. And for example, you enter PIN code and take out the money, and then you walk away. The problem is that a person with an infrared camera can run up to the ATM and just make a photograph using infrared camera. And bigger red means the last number that was pressed, and smaller hot places mean that you pressed that button earlier. And the problem is that anyone can buy for a couple €1,000 infrared cameras so good that they still sense the heat on the buttons even a minute after you have walked away, right? So that is actually a serious issue nowadays. I have a very cheap infrared camera that I use for electronics engineering when I look for whether something is overheating on the PCB, or if thermals are good. And even with that infrared camera, if I, for example, touch something on the table and I look with camera on the table, I can see the fingerprints, warm fingerprints, and that camera costs something like €200, right? And it has a very low resolution, low dynamic range, and so on. But expensive infrared cameras are so sensitive that they can even detect nails in the walls behind the wallpaper, because the metal is a little bit colder than, for example, the wood or the paper. And with infrared cameras, you can actually find nails in walls because of the temperature difference. And they can also be used to see which buttons were pressed by the user on the ATM machine. And in many ATM machines, you just input your PIN code, press enter, and then on the screen, you select that you want to, for example, withdraw like €10 or €20 or €50 using the buttons that are located on the screen of the ATM, right? So the only time you touch the pad was when you entered the PIN. You enter it, take the money, select which sum you want with the on-screen buttons, take the money, walk away, somebody goes up, photographs this numpad, and they have your PIN code of your card, which is really crazy. And then basically what it's a real problem, right? There isn't really any real solution at the moment. But what you can do knowing this is you can, for example, if you want to, and if you're super paranoid, you can just hold finger on other buttons as well as you type the PIN code. So for example, the correct PIN is 1, but you put 3 fingers on 1, 2, 3, and only press button 1. Okay, so all 3 buttons will be warm because you touched all of them. But since you pressed only the first one, hacker doesn't know really which one you pressed. And what ATM machine manufacturers can do is they can use either some material that doesn't absorb heat or material that transfers heat away very quickly, or they can just heat up all of this numpad to, for example, 30 or 35 degrees. So when you touch it, it was warm already, so there isn't really a change in temperature whether you touched it or not. Or the ATM machine can, for example, heat up some buttons and not heat other ones. So as you type them, some are already hot. So when somebody comes up with the infrared camera and photographs, some buttons that you didn't touch will be hot. So hacker doesn't know which ones they were. So, and the PIN code, you can only enter 3 times until the machine eats your card. So maybe it's enough to just give some wrong heat spots to prevent hackers from taking your money. So this is just fun fact about side channel attack. So I guess, and yes, so the same thing applies to cell phone, buttons, and so on. So I guess that's all about side channel attacks. If you have some questions, you can ask. I see there is a question in the chat. If you use gloves, will the heat transfer take place? I would say no. If the gloves are not super thin, then either it wouldn't happen, or it would happen so little that it's impossible to detect it with the infrared camera. So yeah, you can use gloves if you want to. It would definitely help. It's just that, it is now the task of ATM machine manufacturers to come up with such algorithm that even if there's some, regular person not knowing anything about infrared cameras, not knowing anything about, this side channel attack, when they press it, the hacker cannot get this information. So I guess the best solution would be that the ATM machine manufacturers implement some heating of this numerical pad at random places, maybe changing the buttons that are being heated to mix up everything even more, so that the hacker cannot obtain the information. Okay, so do you have some more questions? If you don't have any more questions, then I guess we can finish this lesson, and then we have we have another lecture today at 2:30, right?
Yep.